In this clip, we will develop the notion of equilibrium from the concept of the partition function of a system. Let's consider the following experiment. We have two systems, 1 and 2, both characterized by the number of particles n, the energy, and the volume. In the first step of the experiment, we bring these two systems together and let them exchange energy. In the second step of the experiment, we take the two systems apart again and measure the number of particles, the energy, and the volume after that experiment. Now, if the two systems are in equilibrium, the energy should not have been changed. So that is a sensible concept of equilibrium. So how to tackle this? Well, we again start with the total Hamiltonian of the system, HT, which is the sum of the Hamiltonians of system 1 and system 2. From the total Hamiltonian, we can derive the total partition function, omega t. Now what we are asking is, what is the probability that system 1, after the experiment, has the energy E1? This probability, P of E1, we can determine by counting the number of possibilities that we could configure the system in such a way that system 1 has the energy E1. In terms of a partition function, this would be the integral on phase space of delta E1 minus H1, meaning so we fix the energy of system 1, times the delta function that the total energy E1 plus E2 equals the total Hamiltonian H1 plus H2, divided by the total partition function. Now what we see is that the integrals split up into two integrals, one solely dependent on the phase space variables of system 1, P1 and Q1, whereas the second integral is only dependent on the phase space variables of system 2, PQ and Q2. And those integrals are nothing else like the partition function of system 1 at E1 and the partition function of system 2 at E2 divided by the total partition function. Now we have to realize that E1 is a macroscopic observable. For macroscopic observables, the law of large numbers tells us that the probability of this variable is at its maximum. Hence, the partial derivative of the probability of E1 by E1 has to be 0. So let's calculate this derivative. So we're interested in the partial derivative with respect to E1 of the product omega 1 E1 times omega 2 E2, which is equal to the partial derivative of omega 1 by E1 times omega 2 minus the partial derivative of omega 2 by E2 times omega 1. The latter we obtain by realizing that E1 is equal to the total energy ET minus E2, hence the minus sign. This has to be equal to 0. Now we can rearrange the equation that we obtain, and we find that at equilibrium, the partial derivative of omega 1 by E1 divided by omega 1 should be equal to the partial derivative of omega 2 by E2 divided by omega 2. We can rearrange this further and find that the partial derivative of the logarithm of the partition function 1 by E1 is equal to the partial derivative of the logarithm of the partition function omega 2 by E2. We could do likewise derivations for the two other parameters of the volume and the number of particles. to find the respective result. Our results shows us that the logarithm of the partition function is an important parameter to characterize equilibrium. Therefore, it has been given an own name, the thermodynamic potential, and for the microcanonical ensemble, this is given by S hat, which is dependent on the number of particles, energy, and volume. S hat is directly proportional to the entropy of the system. The entropy S as a function of n, e, and v is given by kb times the logarithm of the partition function, where kb is Boltzmann's constant, having the units Joule per Kelvin. To summarize, two systems are in equilibrium if the partial derivatives of their entropy with respect to any of its variables is equal.